please open to page 187 in your student journal. Today in lesson 6.4, we're going to be looking at some more exponential functions. Today we're not going to graph though, we're going to actually start writing some exponential functions, aka equations. So let's just take a look at question 1 to see what types of equations or what types of situations we're going to be dealing with. In 2005, there were 100 rabbits in Polygon Park. The population increased by 11% each year. So we're going to need to write a function, aka an equation, to represent that situation so we can figure out the population for any years that we'd want to. You guys have written equations before for situations if this would say the population increased by 11 rabbits each year or decreased by 11 rabbits each year. We haven't written equations before where we're increasing by a percent each year. So in order to handle situations where we're increasing or decreasing by a certain percent, we write what are called exponential growth or exponential decay functions. So if we take a look on page 185, at the very bottom we see the setup for an exponential growth function. We have y equals a times the quantity, so times the quantity means in parentheses, 1 plus r, and then the exponent of t. That's an exponential growth function. Now you might be thinking, Miss Golly, that's a lot of variables. What do all those different things mean? Down below, we have each piece broken down for us. The y value is our final amount. So what we're going to have after so many years or so many months, after so much time has passed, that's going to be what we end with. The initial amount, that's the a value in front of the parentheses. Initial amount, you could also label that as your starting amount. Your final amount, you could also label as your ending amount, if you like starting and ending better. The r value that we see inside the parentheses, that's our rate of growth in decimal form. So that means our rate of growth is given to us as a percent. We have to change it to a decimal. So our rate is the percent we're growing or decaying by, decreasing by. And we'll be given that as a percent. We need to change it to a decimal before we put it in our equation. Then the exponent t, t represents time. Time could be years, it could be months, it could be days. Any increment of time. The other form of this equation is if we were decreasing or decaying by a certain percent. So if we look on page 186 at the very top, we have exponential decay functions. And remember, when you see the word function, that's the same as we're writing an equation. The only difference between growth and decay is whether or not we add or subtract that rate inside the parentheses. If we're growing, increasing, we're going to be adding. If we're decreasing or decaying, we're going to be subtracting. All the other pieces are the exact same. So if you look at all of our pieces labeled down below, y is still our final amount or our ending amount. A is still our starting or our initial amount. R is still our rate in decimal form. T is still our time. So let's go back to that example 1 on page 187 and let's put those functions into practice. So in 2005, there were 100 rabbits in Polygon Park. The population increased by 11% each year. So before we start trying to actually write that function, I know it says exponential growth actually in the question itself, but let's pick out why it should be growth. It's going to be growth because it says our population is increased each year. So if we're increasing, we're growing. So when we write our function, aka equation, we have y equals, then the number we put in front of parentheses, that's our starting amount. We start with 100 rabbits. The 1 is always in the parentheses. The 1 represents our starting amount from the year before. It's our percent. The R is our rate of growth written as a decimal. So our R value, our rate's 11%. I need to change that to a decimal. I need to move the decimal point 2 places to the left. And actually, let's go ahead and let's write down what our A value was. Our A started off as 100 rabbits. And then our exponent is our time, and it just tells us after t years. It doesn't give us a specific amount of time. So we just give our exponent a t. So anything you're not given specifically, our y value is the ending amount. We don't know how much we're ending with. Our t value is time, and we're not given a specific amount of time. So that would be our exponential growth function. Then letter B asks us to actually use that function. We want to predict the population in 2025. So we keep our equation the same. And then 2025, that would be 20 years after we start. So we start in 2005, so to get to 2025, our time is going to be 20 years. So our exponent, instead of t, we put it as 20. Now before you try to actually do the computation piece, we can make this equation a little simpler. We can add together the 1 and the 0.11. Now, just like we were practicing when we were making our tables to graph our exponential functions, if we go to the calculator, we can enter in exactly what we see. So if we're making a prediction, we're talking about rabbits, it would make sense that we would round to the nearest rabbit. So if I get an answer like this, I would say that my prediction is, in the year 2025, we would have 806 rabbits in the park. So you just want to make sure that your equation, or excuse me, your final answer, makes sense with the given situation. It won't make sense for me to put 0.23 for a rabbit. So we're going to round off to 806 rabbits. If we take a look at example 2, sometimes we were given a table of values, similar to what we saw when we were graphing, and we want to be able to know, could that table represent an exponential growth or an exponential decay function, or maybe it doesn't represent either one. So in order to tell if we have exponential growth or decay, remember, for exponential, our y values we either need to be multiplying or dividing. If we're multiplying by a number, so if we're multiplying, we're going to have exponential growth. If we're dividing, we'll have exponential decay. So you guys are already used to looking for those patterns of multiplication and division, determining if a table represents an exponential function. Now we're just getting more specific. Is it growth or decay? If we're multiplying, we're growing. If we're dividing, we're decaying. So let's take a look at number 2. Now I might be thinking, okay, Miss Golly, 20 to 30, then 30 to 45, it's going up, but I don't know what to multiply by to get from 20 to 30. So if you're stuck, if you want to see if you're multiplying, take this y value and divide by the 1 before it. So try 30 divided by 20. 30 divided by 20. And we get 1.5. So let's see if our pattern is multiplying by 1.5. So let's take 30 times 1.5. And we get 45. So our pattern is multiplying by 1.5. Pattern's multiplying, so we know we have an exponential function. And since it's multiplying, it means we have growth, that we are increasing, we are growing. So again, to get the 1.5, I took 30 and divided by the y value that comes before it. I took 30 and divided by the y value that comes before it. Let's try the same thing with number 3. Number 3, it looks like I'm decreasing. I go from 160 to 40 to 10. This one, the pattern looks a little easier. 160 divided by 4 gives me 40. 40 divided by 40 divided by 4 gives me 10. 10 divided by 4 does give me 2.5. My pattern is division. So because it's division, I know I have an exponential function. And now more specifically, because it's division, we're decreasing, so we are decaying. If we look at number 4, 32 to 22, then 22 to 12, it looks like we're decreasing, but in this case though, the pattern is just subtracting 10. So if we're subtracting 10, we do not have exponential anything, not growth or decay. If we think back to section 6.3, if our pattern is subtracting or adding, it's actually linear. The last piece I want to talk to you about is if we're already given the equation, like number 6 through 8, we're already given the equation and we want to decide if it's exponential growth or decay, and we want to figure out what's our actual rate of growth or decay. So if we take a look at number 6, if you are growing that means we added in those parentheses the number in the parentheses will be bigger than 1. So this was growth. If you're decaying, that's when we subtracted in the parentheses. So if we're subtracting in the parentheses, that means the number inside of there is going to be smaller than 1. It's going to be smaller than 1. So if we look at number 6, we look at the number inside the parentheses, and we see that it's smaller than 1. Smaller than 1 equals decay. Smaller than 1 equals decay. Now our other challenge is we want to find that actual rate of change. So what's the percent that we're actually decaying by? Remember, what was inside the parentheses was 1 minus r. So we have to figure out how much did we take away from 1 to get what's in the parentheses. So what we can do, we know 1 minus r needs to give us what's in the parentheses. Just solve that little equation. We subtract 1 from both sides. We get negative r equals negative 0.05. So that means positive r equals positive 0.05. Change it back to a percent. Let's try number 7. We look inside the parentheses. Bigger than 1 equals growth. Now to figure out that rate of change, that percent, we did 1 plus r to get what's inside the parentheses. So we have to figure out what did we add to 1 to get 1.08. If you need to, just solve the little equation. Subtract 1 from both sides. R equals 0.8. If r equals 0.8, move the decimal point twice to the right and get your percent. So again, take a look at the number inside the parentheses. Smaller than 1, you're decaying. Bigger than 1, you're growing. To find that actual rate of decay or growth, you have to figure out either what you subtracted from r to get the number in parentheses, or what you subtracted from 1 to get the number in parentheses, or what you added to 1 to get the number in parentheses. So at this time, what I'd like you to do is go ahead, try out your progress check. Use all of your notes to help you out, and then please check it and let me know what questions I can answer for you.